This is lesson 32 on binary to BCD converters. And we've seen how we can display a 4-digit hex number, for example, on the 7-segment displays using X7seg or X7seg-B. But often it's convenient to display these in decimal. So how can we do that? Well, we need some sort of a binary to BCD converter. That is, it will convert a binary number to the corresponding decimal number using BCD or binary coded decimal digits. Binary coded decimal digit is just the digits 0 to 9 represented as 4-bit numbers. For example, here's the hex numbers 0 to F, and here's the corresponding BCD numbers 0 to 9, and then when we get to A, we want to display it as 10, 11, 12, 13, 14, and 15, you see. So 4-bit binary numbers can go up to 9, 1, 0, 1, 0, and then we have to go to the next digit. In this case, the 1 becomes, the tens digit. Well, this is a simple conversion. We could use Carnot maps, for example, to find logic equations for P4, P3, P2, P1, P0 to make this little converter. However, in general, we'd like to be able to do this for any number of bits in the binary number, and there's a so-called shift and add 3 algorithm which will do it. For example, suppose we want to convert 11111111, that is FF, to a decimal binary coded decimal number. Well, we know the answer is 255, so the hundreds will be 2, the tens will be 5, and the units will be 5. Well, the algorithm is to shift the binary number left 1 bit, and then if 8 shifts have taken place, then the answer will be in these hundreds, tens, and units bins here. And if the binary number in any of these BCD digits after you've done the shift is 5 or greater, then you add 3 to that value in the BCD column. And then you go back and shift it again. So you're going to shift 8 times. So let's follow these steps for the hex number FF. That is 11111111. If we shift 1 to the left, it becomes 1. That's less than 5. Shift it again, it's 3, still less than 5. Shift it a third time, we have a 7, greater than 5, greater than or equal to 5, so we add 3 to get 10, 10, 10. Shift them all again. This is 1, so that's less than 5. Here we have 5, so we add 3 to get 8. Shift it again, we have 1, 1, that's 3, less than 5. We have 1, less than 5, so we don't add at all, we just shift again. Now we have 6 in the tens bin, so we add 3 to 6 to get 9. Here we have 3, that's less than 5, so we leave it. Shift again, we have 1, 2, it's okay, 7, so we add 3 to get 10. Shift it the 8th time, and we're done. So we have 1, 0 here, which is 2, 1, 0, 1 is 5, 1, 0, 1 is 5. So we get 255 for the decimal equivalent of FF. So that's how it works. Now, how can we make a logic circuit to do this? Well, we could, for example, make a module called C, which takes 4 bits in, say A, and the output S is either A if it's less than or equal to 5, or it's A plus 3 if it is greater than 5. So we have 0, 1, 2, 3, 4 is the same, but if we have 5, we add 3 to get 8. If we have 6, we add 3 to get 9. 7, we add 3 to get 10. 8 would add 3 and get 11, and 9 would add 3 to get 12. Now, we don't need to worry about A, B, C, D, E, F because those aren't valid BCD numbers, so we can put don't cares here. And you could, if you wanted to make such a module, find the Carnot maps for each of these and actually implement this module. Well, if you had such a module, then you could arrange them this way to do this conversion all as a combinational circuit. So you see how it works. We put in our FF again. Now we can shift it 3 bits to the left because we saw that if you shift it 3 bits, that's the first time you'll get a number that's greater than or equal to 5. In this case it's 7. So 7 plus 3 is 10. And now to shift everything left, that's the same as shifting the C module right. So now we'd have a 0, 1, 0, and we bring down the 1 for B4, which is going to bring down this 1 too. So now the input here is 1, 0, 1, or 5. So we'll add 3 to get 8. Shift by moving this module over. We don't need to add another module here because the maximum we can have is 3 at this point. So now we have a 0, 0, 0, 1. Well, that just stays the same, 0, 0, 0, 1. Now we'll need another module, C6, in addition to C4. We shift them all right 1 bit. So we'll have 0, 0, 1, 1. That's a 3. We don't need to do anything, so that stays the same. Here we have a 0, 1, 1, 0, which is 6. So we add 3 to get 9. 1, 0, 0, 1. Bring down the 1. 0, 1, 1, 1 is 7. Add 3 to get 10. 1, 0, 1, 0. Here we have 1, 0, 0, 1, which is 9. No, the 1 just comes down. So we just have 0, 1, 0, 0, 1, 0 coming into C7, which is 2. So that just comes down. And so we're done. Here we have 1, 0, which is the hundreds, which is 2. 0, 1, 0, 1 is 5, which is the tens. And 0, 1, 0, 1 is the 5. Okay, let's see if we can describe this algorithm in a way that we might be able to implement it, say, in BHDL. Here, this shows the steps of converting a 6-bit binary number to BCD. Let's try 3F. That's shown here, it's all 6 ones. We know the answer is going to be 63. And here's the algorithm. Now what we're going to do is we're going to define Z, a variable Z, say 13 down to 0, that covers the tens and the units plus the binary number. And we'll clear this all to 0 to begin with. Then we need to shift B left 3 bits. 1, 2, 3. We know we have to shift it 3 times before the units can be 5 or greater. And we can say Z 8 down to 3. Here's 8, 7, 6, 5, 4, 3 is equal to B 5 down to 0, 5, 4, 3, 2, 1, 0. So that's the same as shifting B left 3 bits. Now we've already shifted 3 times. We need a total of 6 for this 6-bit binary number, so we have 3 more shifts to do. So we'll do 3 times. We check to see if the units is greater than 4. If so, we add 3. Well, 7 is greater than 4, so we add 3 to get 10. And then we shift Z left 1 bit. So here's our first shift. Now 5 is greater than 4. So we'll add 3 to get 8. And then we'll do our second shift. Well, 1 is less than 4, so we don't add anything. 3 is less than 4, so we don't add anything. So we just do 1 more shift. That's our third shift. And we end up with 1, 1, 0, which is 6, and 0, 0, 1, 1, which is 3. So when we're done, the tens value, 6 down to 4, that's 6, 5, 4, is just equal to Z 12, 9, 12, 11, 10. And the units, P 3 down to 0, is just the Z 9 down to 6. So that's the algorithm that we could implement to convert any binary number to the corresponding BCD number.